Okay, that's funny. Yes, it is. All right. Hello. Oh, there's an audio problem. Sorry. Hang on one second. Yes, your title is well claimed. But sorry, there's some weird. Why does this do? This should not. Sorry. Okay, that for next class topic, we will study the exponential functions of feedback. Wow, that was horrible. Hold on. I think I know why that happened, but sorry. I'll say hello in a second, obviously. Hold on. Okay. Okay, I think that's something. Okay. And I know we want to move fast today. Say hello. Hello, Maisha. Hello, Ruby. Hello. Good afternoon, Andrew. Good afternoon, Weishi. Good afternoon, Zimin. Good afternoon, Manoj. Hi, Leslie. Well claimed, Maisha. Good afternoon, Lizzie. Good afternoon, Catherine. I'm doing okay. Thank you, Mark. Thank you for asking. I'll be more specific about that after a couple minutes and 3 therapy sessions. Good afternoon, Lisa. Hi, Alyssa. Hello, and good afternoon, Jessica. Good afternoon, Jaylyn. Good afternoon, Starnisha. Hi, Michaela. Okay, well said, well said. I would like, all right, so I'm going to, my goal for today is to leave you as calmly ready as possible for, like we do have this exam this evening. It's going to be posted this evening. No later than 8:30 p.m. might be posted a little bit earlier than that if I can get it together. You again, the details are in Google Classroom. Again, it's due back at 3:05 p.m. next Monday. Again, do whatever you want once you get the exam. Do it in whatever stages. Do rough drafts. Talk to your friends, etc. Please do, etc., etc. But then when you hand in the thing Monday before you are my therapy. That is totally true, actually. So when you hand it in, just make sure you're handing in a bunch of white blank sheets that have been scanned that have your name on them. Try to number the pages if you can, but the point is to show all of your work, show that you understand what you're doing, and make it clear to me at all times where you are in the exam. Like, again, your goal is that I'm just looking at your exam and grading it as its own document. I don't even have to cross-reference to the original questions because you've made the original questions clear to me. Okay, blah, 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 blah. Again, once I get rolling today in a minute, it might get a little thick because I'm trying to give you as much help as I can in this last opportunity for the exam. But please, of course, it'll be posted in the video, and of course, the notes will be posted. So please understand that my goal is not to make you feel more intense about it. My goal is to make it to make us feel less stressed about it. I will ask you a couple of questions about that in 1 second, but you just remind me. Oh yes, what I'm putting in the chat before I forget one. I mean, I know I've given you this before, but just in case, that's my phone number in the chat. You can please do text me between Wednesday and Monday. Identify yourself. I'm not going to help with the exam. I'm not like, don't text me like, can you help with question 2? Like, I won't do that. But if you can text a question that takes you longer to write than it'll take me to answer, especially if you think there's an error or a typo or something unclear, or something is unclear to you, you can text me, and if I can solve the problem quickly or help you quickly, I'll be delighted to. And again, also, if you run into any snag, like there's something happening and you detect you're not going to get the exam to me on time, again, let me highly encourage you now, if you have a decision to make, better to communicate with me than not. I mean, if you're on I mean, if you see a problem, let me know. Okay, what I want to do now is, well, certainly any questions you have this period, I want to answer if I can. But my primary goal, oh, can you see? Wait, yeah, wait, I think the answer is yes. I'm actually not even sure if that's a joke or not, but I think the answer is yes. I'm not sure, or unless you mean it as but I think the answer is yes. But I do mean, like, really, if you have an issue about the exam, probably better to text me than to email. Honestly, if you want a fast response, and it also sort of forces it so just as long as you identify yourself, I mean, all of you, whoever you are. And I do want to encourage you again that, probably almost any video that's been posted for this class for 203 for the last like 3 weeks or something is highly relevant to the exam. So even if it's from the other section, I do encourage, I would encourage you to look. What I want to do now is I do want to finish the sort of hard problem that I was going over on Monday. And I want to warn you again, and I've now seen this morning what happened. The problem that I chose to start going over on Monday, what do you call it? The boat in, I'll show you in a second. But anyway, the problem that had a riverbank and a water and a boat, and you had two velocities and we were subtracting them. That problem is thick enough that, it's thick enough that by the time once I start going back to it right now and working it through, I probably won't get too much else this period besides that one. But I don't want that to stress you out. I want to make clear a couple of things. Number one, I've specifically chosen to go over that problem because I really do think it is the thickest, most challenging, most involved of everything in the exam. It's also the most recent material. Like, if you can do that one, everything else in the exam, I think, is more straightforward than that, not more complicated. So that's partly why I'm doing it with you all. And I don't think it's that bad once you break it down, but there's a slight risk in me doing something that long and that hard, today, because I don't want to leave everybody all scared or frustrated or overwhelmed or anything. So I want to ask you, here's a question for everybody. I can continue working through that problem and bring it to completion and finish it and give you the solution to it. I'm happy to do that. In fact, that is my plan. However, here's an option. I did do that in the morning class. It's up to you guys. I mean, I'll take a quick informal vote or whatever. What we could say is that if you don't mind, if you would prefer, I can go over a completely different problem in this class, like the next hardest problem, so to speak. I can go over that in this class, and that way you have that instruction on a different problem, and then you can watch the whole video from this morning. In other words, you would see more material that way, but you'd have to watch the video for that other problem. And I don't know how you guys feel, whether you learn better like when we're actually sitting here together, or whether it's just fine looking at the video. So basically, what do we say? Oh, free float. Yes, I'm sorry. So the question I'm talking about, okay, I'm looking at the chat. Oh, okay. All right. Hang on. So the free float question is the one that we started on Monday, and then I could finish today. And it is, I think, the hardest, most involved problem in the test. But what I'm saying to everybody, Starnisha clearly understands what I'm asking. I just want to make sure she's not the only one. I'm saying I finished that problem, and it took me almost the whole period, but I finished it in the video this morning. So you totally we could do something completely different in the exam. I mean, we could do a different part of the exam, the next hardest thing, and you could watch the video from this morning. And okay, wait. Okay, sorry. Ruby's question, yeah, please turn in this exam to Google Classroom, and please give yourself some time to make sure, try not to wait till the absolute last second in case there is a Google Classroom crash. But right, God forbid, if there's a Google Classroom crash or something like that, yes, turn the exam into my email instead. That is definitely not preferred, but right, if something goes wrong with Google Classroom, or you think you need a backup just in case, to timestamp it. Yes. Do it to my email. Yes. But now, okay. So now I'm definitely getting a vote from Starnisha, which I definitely appreciate. I don't, and I'm going to go with what Starnisha is saying if no one else says anything, but let me just confirm. So like, I'm going to switch gears and do a different problem in the exam, and then you'll watch the video to see the conclusion of the free float problem. And that way you'll have that much more material that's already solved for you for the exam. Is that, I mean, can anybody else, can you at least, can you confirm that you understand what it is that I'm proposing or asking? So, okay, that's two people. All right, so that's Jessica and Starnisha. Thank you. Okay, and I'm going to just take it since they're, I mean, if anybody has a strong objection to, well, maybe it's too late. I'm going to go with what they're saying because they're, okay. Oh, great. Okay, that's three people. That's good enough for me. Okay, and it sounds like we're clear. So so again, the video from this morning, which I think literally has already been posted. I'm not, but if not, it'll be posted right after this class. The video from this morning shows you how to do free float, which I think is a long, hard problem in the exam. And by the way, it gets I'll even warn you right now, it does take a while, like you have to watch the whole video, but it does get fully solved and fully explained by the end. There is a moment in the middle where I accidentally do make a mistake. I'll tell you right now, where I just like put numbers in the wrong order, but then I realize it and correct it. So don't be free. So sorry, like, so it's not perfect, but I corrected it and it's all correct by the end. All right, so you'll watch that, and I'm going to do a totally different problem now. I actually think that's a very wise choice on your part. All right, so I'm going to shift. I'm going to show you where I'm going in the, so bear with me for a second. And frankly, given that we're doing this way, we will have the bulk of all the hard stuff of this done. I think it's fair to say. Okay, so first of all, let me, wait, I'm just looking. I'm going to show you where I'm going. Go to a therapist, go to an unemployment agency. Okay, wait. Okay, no. Okay. Okay. Okay, I'm going to do this problem. I definitely think, I think this is the next hardest problem on the exam. I think this problem may even seem like the hardest, like it seems very intimidating, without a doubt. There's like a lot of reading. In fact, I totally get that. It's actually not as bad once you start doing it, but and I certainly think anything else in the exam that we won't have talked about is more straightforward than what we're doing here. So anyway, this problem here, the YaverBomber, when we begin two dimensions, is what I'm going to go over right now. Okay, so it's page 7 of the practice exam. Okay, and this is kind of like what Maisha said yesterday about the free float problem. In some ways, what's hardest about this problem is even getting straight in your mind what the situation is. Like it does take a bit to see. And so I'm going to tell you what the situation is, but one piece of advice about that is all physics problems are often this way. They give you a big situation, all of these facts. You are supposed to diagram the situation before you begin proceeding. You are supposed to sort of establish the facts before proceeding. But my advice to you as a test taker is, it's true that pretty much every fact that's given here has to be important at some point in the problem. Like otherwise the fact wouldn't be given. But not all facts are needed at all times, right? So do that thing that you presumably used to do when you like study for SATs and stuff like that. Like, don't try to assimilate all of this at once. Get the basic idea, and then as you're being asked the questions, then start looking for the facts that might be relevant to those questions. Okay, don't like that's not cheating. That's being wise. So okay. I'm gonna switch screens in a second and start writing it out. But here's the situation: you've got an you've got an airplane that's flying high, 1,000 meters above the Atlantic Ocean, and it's heading south. Okay, that means it's heading south, which is not the same thing as down, right? It's not heading down; it's heading like south. And the whole jet is 20 meters long. Now it approaches a control tower, tropical Cancer, blah, blah, blah. There's probably all that just means it's heading for a specific point that you might call like X equals 0 in your mind or something like that. It's heading for a line. And as soon as the nose of the plane crosses this line, basically the experiment begins. We could call that time equals 0, and the plane drops a bomb. Okay. A tenth of a second later, the tail of the airplane crosses the line. So what we're trying, and then there's more information that we're going to use later. But the basic idea here, and I'm going to try to draw in a second, is just like you've got an airplane flying in a particular direction, and as soon as the front of it hits a certain point in space, then we begin our stopwatch. As the experiment begins, the plane drops a bomb. It doesn't throw it, it doesn't thrust it, it just drops a bomb, and then it continues to fly. And as soon as the back of the plane has crossed that line, our stopwatches stop, and we stop taking timing meters, and in effect, the experiment is over. Okay, and then like other information is given, but I'm not even going to worry about that just yet. Okay, and so I'm going to be asked a bunch of questions about this. I'll even tell you right now, like what if the details are overwhelming. No, okay. So I'm going to switch screens now. I'm going to draw this, and we're going to start solving it. Assuming I'm, yeah, okay. Just one thing, just remember, south does not mean down. Just remember, okay. Okay, what I am going to do, well, okay, so here we go. Okay. Okay. Sorry. Okay. I know there's other facts about the control tower. I'm going to explain those when we get to them. But this is the basic situation. Yeah, this is the base. I mean, there is a control tower. I'm not drawing it right now because we don't need it yet. But okay. And again, stop me if I'm trying to do two screens at once here, so I'm getting myself a little bit frazzled. But stop me if I'm not being clear at any point. This is the problem, right? So what I've done here is, if I'm keeping track, if I'm like being a student, like to myself, I feel like what I've just done is the diagram and fact pattern. Okay, I might. Okay, actually, I'll be really specific. Okay. What I feel like I've done now is provide all the facts of the problem sort of in my own words, right? Like I clearly didn't copy and paste, but I think all the relevant information of the problem I've now presented here, and I'm sort of saying in English that there's a control tower 400 meters east of the situation. And the reason I sort of wrote that in English is, if you think about it, the best place to put the control tower, like in my picture, would be like popping out of the page, if you know what I mean. Like it, and some of you are better at drawing than most of you are better at drawing than I am. But you know, if the plane is going south, if south is to the right on the page, and I'm making that positive just because that's like the main direction that they're talking about. And I also make, sorry, if I also make on the other axis down positive, because I don't think anything's going to be flying up. I think things are going to be flying down. Then there's a control tower that's sort of popping out of the page to the east. So I've put all the facts. I've put the diagram. That's step one, DFP. Okay, so I'm turning the page now. And then my step two of solving the problem is like, what is the question? And again, you don't have to write WIQ or DFP. I'm writing that for my own sake, but you could if you want to. So question is A, how far south of the tropic right now? This is the question. How far south from the tropic does the bomb land? Now that may seem, I mean, there's a lot of information to assimilate in the problem there. This might seem like a very hard question, but let's just back up and look at it. We've got a plane traveling south. It drops a bomb. What we're asking is, how far south does the bomb travel in the amount of time that it travels? We're asking how far. So in other words, what we're asking is,
Professor?
yes,
I thought we were saying that south and down are not the same.
right, they're not. That's right. You're totally right. So yeah, you're absolutely right. So that's what makes this a real question. Like if south and, you're absolutely right. If south and down were the same, then the answer would be 1,000 meters, because this airplane is 1,000 meters above the ground. But you're absolutely right. So what I'm about to write down, or what I want to say is, what we're asking is, like, this bomb is going to fall. I'm really glad you just said that. the bomb is going to fall down to the ground. It's going to go down. And in fact, it's going to go 1,000 meters because that was one of the givens in the problem, that the plane is 1,000 meters above the ground. Now, while it's going down, I think it's going to be moving forward to the south because it just came out of a plane that's moving forward to the south because of Galileo. I mean, I'll explain that more in a second, but well, maybe I have to explain that a lot right now. Like, what I think is that, let me put it this way, even before we let go of the bomb at all, as the bomb is just sitting there in the plane, it's traveling forward at whatever the speed of the plane is relative to the ground. It's traveling forward. When we open the hatch of the airplane and the bomb begins to fall, there's no reason for the bomb to suddenly attain a spontaneous velocity to the north or anything like that. Like, it's just going to fall. Like, if you look down, if you are standing in the plane and you look down at the bomb, you're going to see it fall directly below you. This is the laws of physics are the same in all inertial reference frames. Like we always say, like, you know, if you drop something, it falls directly below you, whether you're standing on the ground or whether you're in an airplane going 200 miles an hour or whatever. Things fall straight down at all different constant velocities. Like, the laws of physics are all the same. So if I'm standing in the plane and I drop something, it falls directly below my hand and would land on my feet. If I open the hatches and it keeps falling, it's going to keep falling straight relative to me. Again, this is a really important question that he's asking. This bomb is going to fall straight down relative to the plane, which means, like say it was inside the plane, if you were to look from outside and watch it, if it's falling straight down relative to the plane, that must mean it's continuing to go forward while it falls down. And that is true whether it's in the plane or out of the plane. The laws of physics are the same in all constant velocities, in all reference frames. So this bomb is going to continue to go forward while it goes down. And by forward, I mean south. So our question is, how far forward does it go during the time that it falls down toward the ground? Does that, I mean, I'm obviously gonna solve it and everything in a minute, but wait, does that am I making any sense? I don't even know who just, sorry, because I was writing something. Was it Mark who just asked that? I'm not sure who just.
Yeah, it was me.
Okay, so does my answer make sense or no?
Your answer makes sense, but also the way I was thinking about it is, if you have a plane and it lets something go, should the point at which the plane drops something, should that point not be shouldn't that be finite? So the point at which it drops it shouldn't that be the point at which it lands? Or is it because that we're moving at a specific velocity that it also is being carried by?
Right. The second thing, and this is a great question that you're asking, but I think the answer is your second choice. Like basically wherever this bomb is dropped from, I don't think it's going to end up on the ground. If the bomb is dropped, I can't do it in my hands. If the plane is here when the hatch opens and the bomb drops and the plane's moving like that, like the bomb is not going to end up over here. It's going to end up over here.
Okay.
Oh, does that make?
Yeah, that makes sense.
Okay. But everybody, guys, like honestly, and I'm still going to do this. I mean, I'm totally going to do this now. I'm actually very glad we're doing this. It's so good that he just asked that, because you all have to understand, this is the physics of physics. His question is not a dumb one at all, like far from it. Like what you're going to see again when I do this is the math is not the hard part. And I think all of you kind of really know that at this point. The equations, none of you is going to question the equations. What you're going to question is how I'm setting up the equations or why, because what's really interesting about this is the physics of it. And the physics, to all of you, I'm saying, with all of these problems in the exam, like they all seem, and I know they seem different, they seem hard and stuff like that, but they're actually all probing the same idea, which is this idea of relative velocities. I'll put it one other way and then I'll go, I mean, I don't want to, but it is, and this is why, honestly, all of you, why I'm not kidding when I say, please work together on this. It's not cheating. Like the more you work together and the more you debate with the, like even just a quick conversation he just had with me. And of course, we're both interested in time. We want me to get back to the exam. He's being polite and all that. But like if you guys were to debate things like this and really hash it out, like, do you believe me or not what the bomb's going to do? That's what physics is all about. And then you really will rock the exam if you actually like try. So one of the things I'm saying is like, if you walk around the room and you drop a pencil while you're walking around the room, like try it on your own. Like if you're walking around the room and you drop something, I don't think it's going to land behind you. I think it's going to land underneath wherever your hand is by the time your hand gets there. Another way of saying the same thing, but these are all, you got to think about them. But they all do follow from, if you really believe that you're sitting on an earth that's going at 65,000 miles an hour and yet you don't feel it. Like if I can go like this, like the earth didn't move out from under this pen, the pen landed on the earth like where you'd expect, right? We're saying that applies all over the place, all over the time, even when you wouldn't expect it. One last way to put what I'm saying. Again, Mark is not off the topic. And what I'm yelling about right now is not off the topic. I know some of you are thinking, get back to the exam, get back to the exam. But I'm telling you, yes, right. This is relative velocity that we're talking about, John. And to everybody, I am really telling you, I will get back to the exam now. I'm going to give you as many, as much mathematical solutions as I can help. But the reason I do that is I know in my heart that the real thing that makes these exams hard, or the real thing that makes physics is this type of thinking, this question of, wait, so you're saying the bomb would go like this, not like this? That's the physics of the physics. He is asking the right question. And the more, and John is saying the right thing. And the more I can get you guys to actually like take seriously, like, oh shit, wait, you're saying the bomb would go like this, not like this? That's doing physics. And that tells you how to set up the equations. Once you know how to picture it, then you know how to set up the equations and which ones to choose. And the math is not the hard part. Okay, so I'm going to go back to it, but I'm also going to say the principle I'm saying now to Mark's very good question. The principle I'm saying also, it's kind of like if you get to this in lab 4, whatever, I'm saying if I stood on the pitcher's mound and dropped a baseball or dropped a bullet from like I stand somewhere and I drop a bullet, and at the very same moment I fire a gun like next to that bullet, and I fire a gun horizontally. So one bullet just drops straight down and the other bullet goes like 400 miles an hour. I'm telling you both those bullets would reach the ground at the same time. First of all, I'm telling you both those bullets would reach the ground at the same time. Second of all, I'm saying if you get that or can picture it, it's the same concept as what we're saying here. You may have to think it through, but it's all the same concept, which is that the laws of physics are the same in all coordinate systems. Okay, so, but I'm going to go back to this now, but very good question. But let me also say, if I ever lose you today, like obviously you're just going to copy this stuff and you have it on record to study this weekend and to look at while you do the test. But if at any moment today I say something and you're like, wait, what? Please don't get frustrated or stressed. Don't think, oh my God, suddenly I'm confused. And it's like if anything I say today, you're like, wait, what? Then you know what it is to think about for the next 5 days. Like that. Oh, sorry. Okay, wait, I'm gonna look in the chat. But like, if I just run these equations and you just copy them down, you're actually not preparing really in the same way as if I say something that makes you think, wait, that's how the physics works. That's what you want to then spend the next 5 days debating about with other people and stuff. And once it clicks for you, then math will click really easy. Okay, sorry, I'm just gonna look in the chat, but I'm gonna get back to it. Oh, cool. Great. Awesome. Thank you. I totally appreciate it. All right. Everybody should study with him. Okay. So what I'm asking here is how far, and please everybody also, again, remember, watch the other video for the other problem when all this is done and blah, blah, blah. But okay, how far south does the bomb travel? Okay, so what I'm saying is the first question, and this is a little bit, I'll also warn you, this is a little bit unusual that question A is kind of already so hard here of this problem. Like usually we break down and the early questions or the early parts kind of build. I think it was kind of an accident that this A is all of a sudden such a meaty question, but okay, worth doing today. So A is asking, how far south does the bomb travel while it's on its way down? And Well, I'm going to say this quickly. I am saying here that if you're following me, when this bomb comes out of the airplane, if you took a movie of what this individual bomb would do, if you, sorry. Sorry, not to beat a dead horse, but to make it as clear as I can, I'm saying if you watched a bomb from the ground, you would see it go like it would be like a projectile. You would see it go forward as it fell down. It would arc, it would curve to the ground if you watch from the ground, and it would land ahead of wherever it was dropped because it would be falling down while continuing to move forward. That is what I'm saying. If you watched from the ground, because you're watching a bomb that came from a plane that was moving forward. If you watch from the plane, which is a different frame of reference, if you watch from the plane, you're just going to see the bomb head out straight from you, straight down to the ground, which means that wherever the bomb lands will be where the bomb will land directly underneath the plane, wherever the plane is. When the I'm assuming there's not like a major thunderstorm going on or something like that. So the bomb is going to land below wherever the plane is when the bomb lands. It's not going to land below where the plane was when it was dropped, right? That's the misconception that I'm trying to get rid of for everybody. Again, I get that Mark totally gets this now. Like I'm not like yelling at Mark, but it is a very important point. And it's, again, it's more important than any single equation. We don't have that many equations. The equations are not the hard part, but the hard part is knowing which ones apply where. Well, understand that when you drop this bomb, it's going to keep going forward at the speed of the plane while it's going. From the standpoint of the plane, it stays with the plane. From the standpoint of the ground, it moves forward. Okay. Well, last way of putting that, if any of you is either getting frustrated or bored or whatever, if at any moment you type into Google images like B-52 bombers, like World War II aircraft bombers or something like that, that's a fun thing to do. But if you type into Google images, like images of, I could probably do it right now. Well, like, look. Sorry, this is totally. This is actually worth it. Okay, maybe it's not worth it right now, but what okay, I'm gonna go on. Okay, so the question we're being asked is how far does the bomb go south during the time that it falls down? Now, by the way, yes, I don't know exactly what stage you are, but this is precisely lab 4, really, which I know you, whether you did it or not, I posted a video about this like 2 weeks ago and explained, like, this is precisely equivalent to some marble just being shot off a horizontal surface, shot off a desk and moving forward while it falls down. That's what this is. This is a bomb that's moving forward while it goes down. So it is 2 independent but simultaneous one-dimensional problems. Like, this looks like a 2-dimensional problem. We're going to do it by solving 2 one-dimensional problems. Like okay, got you. Oh, I can't look at it now, but I will. Okay. And like 2 things are happening. Something's going forward while something goes down. They're happening independently, like the physics is not affecting the physics equations of one, or not affecting or changing the physics equations of the other, but they're happening at the same time. So the link is time. So what I'm going to do, just like we did in the video about lab 4, what I'm going to do is Okay, I'm first going to solve for the amount of time that it takes the bomb to go from the plane to the ground, the time. Okay, now that is a purely one-dimensional, like I'm just looking at the y-axis. Okay, so I'm just looking at the y-axis right now. Now notice I labeled in the y-axis, you can make whatever decision you want. I made the decision that I'm going to call anything that goes down, I'm going to call it positive. You might think that's weird, but I'm thinking nothing is going up. Anything that's going anywhere in the y-axis is going down. I want as few negative signs to deal with as possible. So I'm calling anything that goes down positive, okay? This bomb is free falling, like just like lab 4. It's accelerate, it's free falling. It's falling. Nothing is affecting it besides gravity, but gravity is affecting it. So the acceleration in the y direction, right? The acceleration in the y direction, if you like, is constant. It's the very same as whatever the acceleration was initially, and that's the acceleration due to gravity, which you could call approximately 9.8 meters per second squared, or you can even round to 10 meters per second squared, which I highly encourage that you do. And it's written in the front sheet of the test. It's totally fine to round to 10. It makes our life easier, but that's fine. And I'm calling it positive because it's going down, and anything going down, I'm calling positive, right? And the initial velocity in the y direction is 0, just like lab 4. The initial the initial velocity in the vertical direction is 0 because this thing was just dropped. It wasn't thrown down. It wasn't thrown up. It was just dropped. Now, granted, I know it's moving to the x, but that's the x direction. We'll deal with that separately. We'll deal with that independently. In the y directions, the fact is we've got some object that's in free fall from rest. Oh, and one other fact, and we also know that it falls 1,000 meters. I believe it's 1,000 because that's what that's how high the airplane is above the ground. It was given in the problem. Hold on a second, I'm just responding to chat. Okay, so those are our facts in the y direction. Notice the key here is separating the axes and just dealing with one axis at a time. I'm sorry, I'm okay. Okay. Sorry, something happened. All right, so in the y direction, I could use any equation that could work, any of our equations that we have so far that we understand. Here I have a situation where I know the time, I know the initial velocity, I know the acceleration, excuse me, I don't know the time. I know the displacement, I know the acceleration, I know the velocity, I'm looking for the time. I have various options, but we spent some time deriving this equation because we said it was a good shortcut for situations like this, right? And I'm putting little y subscripts. These subscripts just to remind me that I'm talking about the y-axis, okay? Right? So this is the equation I'm going to use. Now notice this, in the y direction, the initial velocity was 0. We just said that on the previous page, right? So we just have in the y direction, we have y equals 1/2 at squared. I'm solving for t, right? So my suggestion to you, and by the way, now we could even say, this, if we're trying to keep track of like solving the problem, like this is step 3, general definitions and principles, right? Arguably. And now this is, I'm doing step 4. I'm like doing a particular application and work. Again, you don't have to write those things out, but I'm just showing you that that's what I'm doing. Notice that I'm postponing the numbers for as long as possible. Like I'm going to rearrange this now and say, okay, t squared equals 2y over a. T equals square root of 2y over a. And y we said was 1,000. Tell me if I'm wrong about that, but I think it was 1,000. and A we're saying is approximately 10. Again, you can round to 10 in the exam. The only place that's not really good to round 10 is like in your lab if you're really trying to get precise. But anyway, you get it. So we have square root of 2,000 over 10. That's the square root of 200. We'll go on the next page. I could stop me if you want me to go back a page or anything like that, but so far, so. Now I keep saying this is like lab 4, or at least like the video that I posted about lab 4 last week. But please notice it's also like the Wile E. Coyote Roadrunner problem. Same thing happened. We had, oh yes, absolutely. Thank you for asking. Thank you. Yes. I think I can. Yes. Okay. God, I love that. So when you guys ask me to turn back a page, it makes me so happy. It literally makes me, you might as well just say, Professor, you still exist. What you're doing is actually meaningful. So thank you. Yes. I'm going to just talk while you look at this page. Notice when we did the Wile E. Coyote problem, the first problem we went over in the exam, looks completely different, right? Totally different situation, looks like totally different physics, but it's really, oh, no problem, awesome. It's really the same deal of like there, something was falling down while something was going over, and it looked like all these complexities, but our main principle was to say whatever's going on in this axis does not affect whatever's going on in this axis. It's just that they're happening at the same time. So we used one axis to solve for time, and then we plugged that time into the other axis. Now, in that case, a little complexity was that we solved and we got 2 times, like because the Roadrunner went there and then came back. That like every problem is different. But really see that we're really doing, it's like the same thing that's happening over. Once you get used to it, you see it really is all one fundamental concept being played out. But anyway, so what I just got was the time to the ground. Now, there's only one answer here because the bomb is like the bomb didn't shoot up, it's just going down. So we get approximately 14.1 seconds to the ground. Okay, now what was our question? Our question is, how far south does the bomb travel in that time? So now I'm going to switch to the x-axis. And by the way, the hard work has been done definitely for this now. Okay. Oh, so I'm in the chat. Okay, cool. Okay, now we go to the x-axis. Now the truth is, and again, I hate to keep saying it, but really this is secretly lab 4. And even if you never finished it or you didn't, I mean, what this is just someone firing something off a horizontal surface and then that thing landing on the ground. That's what's happening here. So the x-axis, we have different information, but again, we just focus on the x-axis independently now. We look at the x-axis, what's happening in the x-axis? Well, first of all, there's no acceleration in the x-axis. In truth, the x-axis is easier to deal with ultimately because there's no acceleration whatsoever because gravity doesn't pull things to the south or to the north. Gravity pulls things down. There's no gravity in the x direction. There's just a plane that's going along at constant velocity, we were told. It's going along at constant velocity. And there's no reason for that to change. I mean, it's constant. So the bomb that comes out of this plane, the bomb, like basically what I'm really saying is each axis is independent. So on the y-axis, we dropped something. In the x-axis, we didn't do anything at all. I mean, in the x-axis, what we did was, I mean, in the y-axis, we like let go of the floor. So the thing supporting this bomb was no longer there. So the bomb started going down. But we didn't do anything in the x-axis. We just have a bunch of stuff going like this. And then at some point, it decides to also go like that. We just added a y component of motion to this thing. But a bomb was going along, and it's just going to continue to go along. Because for it not to, there'd have to be some kind of force or influence or acceleration or something against it to slow it down. Like if there were huge wind or something, we might be able to slow this bomb down. But no one said there's wind here. There's no wind here. The bomb is just cruising. The bomb is going to do exactly what it would do in the airplane itself, which is just keep on going. The law, and you might say, but wait a second. Like once the bomb's not in the plane, then why does the bomb, you might say, but shouldn't the bomb just want to sit still? And it was only traveling forward because it was in a plane. Now that it's not in a plane, shouldn't it want to sit still? Shouldn't it not want to move forward anymore? But no, nothing wants to sit still. Nothing is in the world sitting still. Things are sitting still relative to other things, right? You know what I'm saying? Like the airplane is its little physics lab, just like planet Earth is a physics lab or a coordinate system, and the sun is a coordinate system. The bomb didn't think it was sitting still when it was in the plane, and it's not going to think that it's sitting still when it comes out of the plane. The bomb is just doing whatever it's doing relative to everything else. So the bomb keeps, what I'm trying to say is that the bomb horizontally should just keep going horizontally at whatever horizontal constant velocity the plane had. Do we know what that is? Well, directly, we don't. We were never told directly that the plane had like a speedometer that said 400 miles an hour or something. But what we were told, and again, this is just like lab 4, what we were told is that when the front of the plane passed a certain line that was all complicatedly called the Tropic of Capricorn, blah, 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 who cares? It passed a certain line, which is like a photo gate. It passed a certain line and a stopwatch started. And then when the end of the plane passed that line, the stopwatch stopped. We were told the plane is 20 meters long. And then it took the entire plane a tenth of a second to pass a certain line. That is just like saying it takes an entire marble a certain amount of time to pass through some laser beam in a photo gate or something. In other words, if you think relativity, think of that line. I called it the Tropic of Cancer. It doesn't matter what it's called, that line of latitude or whatever. Just picture like a line, drawn in the sky or drawn on the ground. If you think about it, if you're in the plane, you see the line come to your face, come to the nose of the plane. And like if you're in the plane, just watching the world, you watch the line come to you, and then it passes you, and then eventually hits the back of you, the back of the plane. Right. So that from your perspective, that line traveled a distance of 20 meters, and it did so in 0.1 seconds. So relativity, that means that that's how fast the line was moving past the plane. That's therefore how fast the plane was moving past the line. You see, it's just the same concept over and over again. But anyway, so I'm saying, what is that? So that number is 20 divided by 1/10. So it's 200 meters per second. So I'm saying the constant and therefore average and therefore instantaneous, like the horizontal velocity of the plane is 200 meters per second, right? It has no acceleration in the x direction. It just has a velocity of that in the horizontal direction. Therefore, That's not exactly. Okay, I'm saying the answer, and again, this is a little bit long, a little bit involved, maybe, but I think actually possibly one of the more involved questions of the question. The answer is that the bomb lands 2,820 meters south of the original tropic. Now, again, to be totally honest to all of you, this question would probably be 20 times easier if the words were east and west rather than south and north. That was, I don't know if there's a mistake or it was an over. I mean, part of what is confusing is it's very easy, even unconsciously, even if you hear me say, it's very easy to think of south as down, and and it also makes it harder to draw the pictures. That might be throwing some of you, and that's not on purpose. And maybe I'll even change it in the actual exam. Like it's just, but it is reality. But I'm saying, just think of south. South is just a direction, right? I mean, south is just a direction, like north or east or west. I'm saying this plane was flying south. It dropped a bomb. While the bomb is falling down, it's moving forward south. How far forward did it move? Exactly. In other words, the bomb is 2,820 meters ahead of whatever place the plane was when the plane dropped it. The place that the plane was when the plane opened its hatches was this place called the Tropic of Cancer. So what we're really saying is, when the bomb hits the ground, 14 seconds later, the plane is 2,820 meters ahead of the tropic, south of the tropic, and so is the bomb. That's what we're saying. It's just that the plane is still in the sky and the bomb is on the ground. Okay, that's the answer to that. Cool. Okay, yeah, wait, can I? Oh, yeah, great question, Andrew. Yeah, because there's no gravity, because gravity is the only reason there's any acceleration anywhere in this problem is the acceleration due to gravity, which is only a downward pulling thing. Like basically in life, in physics, and we're going to do this next, for there to be acceleration, there has to be a force or an influence, a push or a pull. Things, according to Galileo, things don't automatically accelerate. They only accelerate if they're forced to. And the only thing in this whole problem that's forcing anything to accelerate is gravity. And that's the only thing in the exam that will ever, and that's pulling only down. There's no gravity in the forward direction, if that makes sense. Basically, because we're told the airplane is making sure to be cruising. The airplane is cruising, therefore the bomb is cruising. I don't know if that answers or not, but great. Okay, cool. Okay. So that's that one. We still have 15 minutes, which is good. Okay. I think the problem mostly gets like and honestly with you guys, again, a lot of physics problems, like, the early steps, the early parts are like steps that you do, and then it builds to the end. In a way, this one is sort of funky in that this one's forcing you to get the concept right away. It's asking you to like really picture the concept correctly. But if you are picturing the concept correctly, and if you followed what I just said, then keep that concept in mind. And for the rest of this, it won't be that bad. Okay, so I'm gonna be able to race, not race, but I'll be able to do this. All right, so now we're on B. Sorry. Okay, B is like a conceptual question. Okay. Okay, so what we're getting into this whole elevator cage thing. Like, let's not get intimidated. Let's just like read back. Oh, sorry, you can't. So B, sorry, I keep forgetting which screen I'm on. Okay, in fact, Okay. So what I'm reminding. Okay, so what we were told in the original fact problems of the problem is that there's this control tower that's like east of the place that this is all happening. It's sort of hard to put in the diagram, but it's like, there's a control tower also on the ground, in other words. And what we're being told here, or what we're told in the beginning and sort of told in part B, is that just imagine that the moment that the airplane drops a bomb, at that very same moment, an elevator cage free falls from the exact same height. Okay, like total coincidence. Right? The airplane drops a bomb and an elevator cage literally, like something snaps, it breaks, so it free falls directly, vertically, no tricks, from the same height. And what we're and to the same ground. So the question here of question B is, I'm being a bit fast here with 10 minutes left, but basically what the question asks, and you might want to word it a little bit more carefully than I am here, but it's asking which of these two objects, the bomb or the elevator cage, is going to hit the ground first. If they were both dropped from the same height at the same time, which is going to drop first? And this is the thing that I was like yelling about 5 minutes ago, sort of forgetting that you were going to be asked to anyway. So you might think this is obvious. I don't know. But the answer is they're both going to hit the ground at the same time. They're both going to hit the ground at the same time. And maybe you think that's obvious at this point, and good. But the reason it's even a question at all, the reason it's even like worth pondering as an issue is we have two objects here that started from the same height, and one fell straight down and the other went down in an arc like this. Again, this is equivalent to me dropping a bullet and me firing a bullet at a really high speed horizontally from the same height at the same time. What we're saying here is if you really understand that each axis is independent of the other, that gravity is in the y-axis, but it's not in the x-axis, and that the amount of time it takes you to hit the ground is simply determined by how high off the ground you are. I mean, it's simply determined by y equals 1/2 at squared plus b naught t to the ground. In other words, the equation that we use to solve for the time for the bomb is the exact same equation we would use for the elevator cage, and all the same numbers would apply. V naught is 0 for both of those objects in the y direction. The only difference between the two objects is that one of them has a V naught of something very large in the x direction, but x doesn't have anything to do with time to the ground. So basically I'm saying, and you do have to explain this in your words, but I'm saying the answer to this one, to question B, both hit ground at same time. So that's B. I'm looking at the time, so 9 minutes. Okay. And again, I know I'm like yelling and maybe I'm going a little, I don't know if I went too fast or too slow, but stop. But then C. C asks, when should the first, now C starts talking about other bombs being dropped. We'll get to that in a second. But C, literally the question of C asks, when should the first bomb hit the ground? Well, we answered that already. I mean, C is when does bomb number one, the one that we've been talking about, hit the ground? Well, we figured that out. The end, and you can literally say C A above time equals 14.1 seconds from drop. Like we figured that out already. Okay, so that's the answer to C. Again, I'm just, well, you have to do things your way, but then D, oh, what? Oh, okay. Then D asks, how far apart are the bombs? Where D asks, okay, so what it says now, and again, I'm just trying to go a little bit fast here. What it says now is imagine that after we dropped the first bomb, we waited 3 seconds to drop the second bomb. Okay, again, same way, just vertically, but imagine that the bomb fell down, the bomb that we already figured out, and then 3 seconds later, there's another bomb. It wants to know now how far apart will they land on the ground? And they will, right? And if you really think about it, if you really think of, well, anyway, they'll be spread out on the ground. Each bomb's going to land in a different spot on the ground. And the answer is this. And so that thing we first figured out, like 2,820 meters, that was figuring out how far will the bomb be away from its original dropping point, i.e. the Tropic of Cancer. What we're now asking is, if you dropped another bomb, how far behind will that second bomb be from the first? So it's not the same question and it's not the same answer, but it is just as simple. Here it is. Right, I believe we said that the bomb's velocity, the horizontal velocity, yeah. We have figured out that these bombs are moving forward at constant velocities of 200 meters per second, each one of them, because that's what the plane is doing. Each one of these bombs is moving forward constantly at 200 meters per second. So if one bomb drops and lands on the ground and then you wait 3 seconds and you drop the next one, it means they're going to be separated by 600 meters. It's that straightforward. I'm going to keep, right? Like that's, and what I'm really trying to say is that this all looks very complicated. I think it does look very complicated. We're trying to show that there's much more simplicity underneath the surface than you might expect. But it's not simple if you over mathify all of this. It is simple if you really think through the physics concepts of it. Like the math is not the hard part. And by the way, that continues to be true, really, in a way, with physics. Even when the math is the hard part, it's not. But okay, so 600 meters is the answer to question D. Then E, and we're almost done, believe it or not. Yeah, and E, okay, I don't know if you're looking at the test with me, but E and F, for some, it's not two different questions. It's one, I can't correct it now, but E starts describing, it says, imagine that the thing continues to bop. E says, imagine that the plane continues to drop bombs identically and in succession. It drops a new one every 3 seconds. Imagine that there's a photographer like taking pictures, and then F, it just says, so there's no question E. There is no question E. It's just a misprint, sorry. But F says, how many bombs? What? Oh, sorry. Hold on one second. Sorry. Thank you so much. Sorry. You too. Okay, so, how many bombs in one picture? I'm going to do this fast and we're going to be done. Go to 420, right? Yeah. How many bombs in one picture? All these last 3 questions are all about the same thing. So I'm going to write them out. F says, how many bombs in one picture? G says, how arranged? I'll explain what I mean here. And H says draw. Okay, this is what it's getting at. And this puts it all together. This is the ultimate thing. It's imagine this is where I was going to say before, if you go to Google Images and you just type in like World War II bombers or B-52 bombers or something, you can see pictures of this type of thing. If the plane is going along and it drops a bomb, and then it drops another bomb, and it drops another bomb, and does it in a nice normal pattern, like no tricks. It just keeps dropping bombs at equal time intervals. If you were to take a photograph here's my drawing. If you were to take a photograph of one snapshot in time of this plane doing this, at some snapshot, you would see something like this. You would see, and this is key, you want to think about this when this class is over, like this. If it might make immediate sense to you, or it might throw you. Frankly, if it throws you, that's good, because it means you really are thinking and you should think about this. I'm saying if we took a movie of any individual bomb, a movie of an individual bomb would be falling in a curve. It would be going down while it goes to the south, and it'd be going down faster and faster while it goes to the south at a constant velocity. So it would fall in a curve. But if we just took a picture, if we were dropping bombs out of the plane, and dropped one and it kept going, and then dropped another and kept going, so that there were a bunch of them accumulated under the plane before they all hit the ground, we would see them lined up in a vertical line. That actually probably is a surprise if you really think about it, but it is what I'm saying, that they're all staying with the plane. They must be. This is Galileo's principle of relativity. I mean, especially assuming there's not like a thunderstorm or something. They're all going to stay with the plane in a vertical line. The drawing would look like the drawing I just gave you. They would be arranged. In other words, the answer to this is vertically. They would not be dragging behind, and they would not be dragging forward. Each one of them is moving forward while it falls, just like the airplane is moving forward while they all fall. They're all moving together forward at the same rate while they fall down. Okay, so as to how many could be captured in one, so the answer, so that's the key. If you get that, if you can understand why a photograph of all the bombs would be a straight vertical line underneath the plane, and that's another way of saying if you get that, and yet you get at the same time why a movie of any individual one would be falling in a curve, then you really do get this. And the only other question I have to answer, and then we'll go, and good luck tonight, and blah, 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 is how many bombs in one picture? Well, well, the answer is basically 3, because one picture contains 14.1 seconds, like it takes 14.1 seconds for a bomb to fall to the ground, right? And they're being released every 3 seconds. So once 14 seconds has elapsed, a bomb has hit the ground. So how many times does 3 go into 14? A little bit more than, so it's four bombs, sorry. So 4 bombs. And that's the answer. I'm going to stop right there. Okay, if there's any I'm not going anywhere. I do have another class in 5 minutes, but I'm going to be here if there's any questions. Again, you have my phone number if there are any questions. I think we really have now covered certainly all the, we've actually gone over a lot of the exam. And I promise you, anything else in the exam, you certainly have all the equations and you have the concepts. And I think anything else in the exam is actually a little bit less complicated and less hard than what we've gone over. So it'll be posted in a few hours. And I thank you very much. I will turn off the recording, but I'm here. Thank you. Have a great week. Great questions. Oh, thank you. Awesome. I'm glad to hear that.